tonight. Welcome everybody to Wednesday Night at the Lab. I'm Tom Zinnan. I work here at the UW-Madison Biotechnology Center. I also work for the Division of Extension Wisconsin 4-H. And on behalf of those folks and our other co-organizers, PBS Wisconsin, the Wisconsin Alumni Association, and the UW-Madison Science Alliance, thanks again for coming to Wednesday Night at the Lab. We do this every Wednesday night, 50 times a year. Tonight it's my pleasure to introduce to you Benjamin Zuckerberg. He's a professor in the Forest and Wildlife Ecology Department, Russell Labs, dearly beloved Russell Labs, where I studied from 1982 to 1985. He's going to talk with us about winged sentinels, how birds are coping with climate change. I'm now going to ask you the classic 5 questions, so if you'd like to come over here.
Oh, no.
Oh, yes. You'll be able to pass them if you're not.
Okay.
Where were you born?
Brooklyn, New York.
And where'd you go to high school?
Packer Collegiate Institute.
In Brooklyn?
In Brooklyn.
Way to go.
Thanks.
You didn't grow up in Queens.
Yeah, I know. That's true.
And then where'd you go for your undergrad and what did you study?
Connecticut College. I majored in zoology, studying with the great Robert Askins.
And then for your advanced degrees?
I got my master's at UMass Amherst, and I got my PhD at the State University of New York College of Environmental Science and Forestry. And then I went and did my postdoc at the Cornell Lab of Ornithology. And then I came here.
So if my mother-in-law is working, she is watching. We both begin with W. She went to UMass Amherst.
Excellent.
She's the one who gave me this blue shirt.
Nice.
That's why I wear it. Because, you know, when your mother-in-law gives you something.
You got to wear it.
Absolutely. A lot of folks here are looking forward to this talk. I got to ask you, is winged one syllable or 2 to you?
Oh, it's a good one. I would say that's 1.
All right. There we go. Please join me in welcoming Benjamin Zuckerberg to Wednesday Night at the Lab.
Great. Well, thank you all and thank you, Tom, for the invitation to come speak with you all today. And greetings to everyone joining us online. And so, yeah, today I'm going to talk about this question of how birds are responding to climate change. But I'm going to start off with sort of a broader hypothesis and a framework that I've been developing over really the last 25 years. And that hypothesis is this. Sorry. It's not clicking. Yeah, I'll just use spacebar. My hypothesis is that birds are awesome. And I have a number of lines of evidence to actually support this hypothesis. One is that birds are clearly numerous, right? We've got a number of species that occupy really a vast diversity of ecosystems throughout the world. They occupy the Arctic tundra. They go all the way down to tropical rainforests. Birds are amazingly diverse, right? From sort of hummingbirds all the way up to vultures and eagles. They really are sort of amazing in sort of their different life histories and how they show up in terms of their adaptations. They show pretty amazing behaviors, right? So we can think about tool use in some birds, and clearly how they may use certain supplemental foods and novel food resources. And really one of the most amazing things birds that do, they clearly can adapt to pretty amazing and novel ecosystems. But I like to say I came up with this, but obviously there are many cultures and societies out there that clearly see the value and the beauty of birds. And they've incorporated them into their own culture, their art, their folklore, and their songs. And so clearly birds play a very important role in our society and our cultures at large. Unfortunately, it's not always a good story, because what we know with birds is that they are being faced with what is relatively a new sort of suite of anthropogenic stressors. And because of that, birds have always been those sentinels that canary in the coal mine as to when potentially the ecosystem or the natural world is being threatened. And certainly over the last 100 years, many of these canaries in the coal mine have been threatened. They've been threatened by habitat loss and fragmentation. They've been threatened by air pollution. They've been threatened by overhunting and persecution. And they've been threatened by domestic pets like outdoor cats, as well as invasive species like rats. And because of this, since the 1970s or so in the United States, we know that we've lost roughly about 3 billion birds from the United States a month. So superimposed across this sort of deadly sort of cocktail of anthropogenic threats, though, is a pretty amazing one that's occurring right now. So what you're seeing here is temperature data stretching back to the late 1800s. And what I want you to see here in sort of the Earth's climate and its variability from one year to the other is roughly around the 1970s, you're going to see a pretty remarkable shift in the Earth's climate system. So right about here, you can start seeing what has been sort of a rapid and pretty significant warming throughout the world. And if we actually look at that warming here, there's a couple of really important characteristics that jump right out. One is that it is relatively uniform, right? There's very few areas of the world that are bucking that trend, let's say they're getting cooler. The other component here is that some areas in the northerly sort of latitude, especially the Arctic, are warming at a rate that is sometimes 2 to 3 times faster than we're seeing throughout the rest of the world. And so what we've seen over, certainly going back to the late 1800s, is that the world is about 1 degree Celsius warmer than it was back then. So to put that a little bit in perspective then, is that if you actually are able to reconstruct global temperatures over the last 2,000 years, what we can see is that in the last 30 to 40 years, that rate of warming is really unprecedented over the last 2,000 years. And in fact, if we stretch it back even farther, when we look at the late Holocene, which was a period of deglaciation considered to be a relatively warm period in the Earth's climate history that stretched out thousands and thousands of centuries, that even that period, about 100,000 years or so ago, really was considerably warmer, but we are getting to that level. I think it went back. Yeah.
Next one. Yeah, okay, good.
When we drill down on the United States, and what we can see is that some areas are certainly getting warmer faster than areas. So what we see globally is actually occurring here in the United States as well, where areas such as the Western United States is getting warmer, and clearly parts of the Northeastern United States are also getting warmer. One of the real telltale signs of this is that every decade has been basically warmer than the one previous to it, going back to the 1970s and 80s. The only area that seems to be sort of showing a different response is what's called this warming pole in the southeast, where it's not warming quite as fast. But what I would tell you is that most of the current observations suggest that that warming pole is beginning to close and catch up with the rest of the United States. Precipitation tends to be a little bit of a mixed bag. But overall, throughout the US and many parts of the world, we're actually seeing a wetter world and more precipitation and higher rainfall. We're seeing more flooding events and more extreme rainfall when it does happen. But clearly what is also happening, especially if you live in the Western United States, is very prolonged drought-like conditions. And we're actually considering these to be sort of mega drought events that persist much longer, and then of a higher magnitude than really anything that's ever been previously reported. So what they say, and what we're beginning to see in terms of these climate data, is that dry areas are tending to get drier, and wet areas are tending to get wetter. At the same time that we're seeing these temperature records, and clearly one of the other sort of mechanisms or other patterns that we're beginning to see is CO2 in the atmosphere, carbon dioxide. And one of the really remarkable parts about this is that if you look at carbon dioxide records and reconstructions going back 800,000 years or even 20 million years in some cases, it really gets above this level of about 400 parts per million. Right now, we are at 413 parts per million in the atmosphere. And under almost every single projection that you see here, and these are sort of future CO2 emission projections, that even under sort of the best case scenario, that we're never really going to get below that 400 parts per million. And some of the worst case scenarios, we're getting along sort of 600 or even 800 parts per million. A pretty amazing thought experiment is this idea of the pulse. which is that effectively, if we stop basically bringing fossil fuels out of the earth like today, and we basically burn all the fossil fuels that we have in gas tanks and power stations, and we just kind of ran it all one day, this is what the parts per million would be. About 2,000 parts per million, just for basically burning all the fossil fuel that we already have available to them. And over time, it would take roughly about 1,000 years for even it to start declining. So this relationship between CO2 and temperature is a very well-known one that really goes back in time, not just sort of in our contemporary climate system, but looking at past geological events as well. So it's not just temperature and precipitation then. Really what we know to be happening is that CO2 concentration is the highest in at least the last 2 million years. The sea level rise is sometimes at its fastest rate in at least the last 3,000 years. That the Arctic sea ice, the area sort of sea ice extent, is at its lowest level in the last 1,000 years. And glaciers are retreating at an unprecedented rate that is not even comparable for at least 2,000 years. So taking all these sort of signals together then, the real statement from the IPCC, which is the Intergovernmental Panel on Climate Change, basically suggests that it is unequivocal that human influence has warmed the atmosphere, ocean, and land. We don't debate this anymore. It is widespread and rapid changes in the atmosphere, ocean, the cryosphere, and the biosphere have occurred. So given all that, all those trends that we've been able to document, then we are left with this question: how will birds respond? And ultimately, when we think about this question, birds basically have three responses, right? One, we know that birds are capable of pretty amazing things in terms of their movement. And so clearly, if their climate space is changing, the birds can actually move with that climate space. Alternatively, if a species cannot move, and maybe there's different reasons for that, right? Their food resource isn't there, maybe there's a predator, maybe there's some sort of obstacle or mountain chain, then their other sort of response or the other pathway is that they can adapt, right? So as their climate space changes, then they potentially can adapt to those new climate settings. And then a third is if they can't move and they can't adapt, then clearly they're facing extinction. So today I'm going to kind of walk you through what I consider to be sort of the 5 most principal sort of responses and storylines of how birds are responding to climate change. I'm going to tell you a story about behavior. I'm going to tell you a story about range change, changes in phonology, changes in potentially population declines, and ultimately thinking about disease transmission in birds and how all these things are mediated in one way or another by climate change. So first, to start off with this idea of behavior, and I'm going to actually take this sort of story first from a very local sort of perspective. One of the real changes that I didn't talk about in terms of trends in climate change is the loss of snow cover. So if you're looking throughout the whole northern hemisphere, and you're looking at the extent of snow cover, frozen ground throughout the whole northern hemisphere, we've seen a pretty amazing change in that sort of snow cover extent. Starting roughly about the 1980s, it has gotten less and less and less, okay, which would make sense under a warming world. But when you start looking at the magnitude of that loss of snow cover, it's pretty remarkable. We're losing roughly about 4 million square kilometers of snow cover extent every decade. What this amounts to is basically the area the size of Texas. Okay, so if you're a species that's specifically adapted to snow cover, then that's really a habitat loss that is on par with something like tropical deforestation. And we are seeing that same type of snow cover change and those changing snow cover dynamics right here in Wisconsin as well. And over the last several years, and going back to 1970 or so, we've seen roughly a loss of about 20 days in most parts of the state of permanent or seasonal snow cover in the state. So what does this mean? Well, clearly, if you're a winter adapted species, then this can have potentially strong implications for your behavior, right? And one of the species that we think about in terms of having pretty unique behaviors with respect to snow cover is this guy right here, the ruffed grouse. So ruffed grouse are one of those sort of northerly distributed species. They kind of occur throughout much of Canada, and they meet their distributional sort of their range limit is kind of right here in the upper Midwest. Okay, And they are a hardy bird, absolutely. They can get through the winter environments. And in fact, they do this really amazing behavior, which I'll kind of show right here. So if you're walking along the forest in winter, so where was that grouse that suddenly appeared? It was under the snow, right? So grouse do this very unique behavior called snow roosting. So a lot of species will actually spend a fair amount of their time, especially during the winter, in this behavior called roosting. And it's where they kind of basically huddle down. They kind of don't do much foraging. They don't do much movement. And it's really to preserve energy, to avoid predation. And when you got few resources, you're really just kind of huddling and kind of getting through that winter environment. So grouse can kind of do this in a couple of different ways. They can roost definitely on the ground, right? So they can find these sort of bushy and understory areas and kind of hang out and cuddle in there. They can go up into the trees, right? And that's certainly possible for them, and they can roost up in those trees. And at the same time, they can take advantage of snow, and they can either kind of create these what's called snow bowls, where they kind of shuttle down into the snow and then kind of create this depression in the snow, or in some cases, they'll either walk into the snow, down into deep snow, or they'll fly up and then dive bomb underneath the snow, right? So why would they do this, right? Why would they kind of take this sort of very sort of specific type of behavior to take advantage of the snow? Well, it's kind of two reasons. One, clearly, if you're a grouse and you're kind of like we just saw, hidden in that snow, you can avoid predators, right? So that's definitely an advantage. But another really significant advantage is those snow roosts tend to be about 7 degrees warmer than certainly those ground roosts. So what happens here is that once you get enough snow on the ground, roughly about 7 to 8 inches of snow, that snow actually becomes, that area beneath the snow becomes thermally stable. It's almost like a blanket. And so when those grouse are in there, they're generally a lot warmer, or experiencing much warmer temperatures, and then those temperatures are much more stable. So we were really interested in trying to tease out really what is the benefit of this, right? And so we followed a number of different grouse over several years up at Sandhill Wildlife Area, which is near Babcock. And we wanted to see whether or not there is this effect of being able to use the snow roost. So one of the first things we were able to discover was that when it is cold, the corticosterone levels of these grouse shoots up. So corticosterone is a stress hormone. We all have it. When you're really stressed, your corticosterone levels shoot up. If I'm about to give a talk, my corticosterone levels are kind of ramping up, right? And what we were finding was that these grouse, when they're exposed to really cold temperatures, have these really high stress levels. Okay, so how or why would this be sort of important for them? Well, those that were able to take care of those snow roosts or take advantage of those snow roosts were actually able to decouple from that temperature effect. Their stress levels remained relatively stable. Okay, which is what we'd expect. They're taking advantage of that thermal area. And when we start thinking about this effect at sort of a broader population level of this stress effect, what we were really interested in was whether or not they had increased survival. And that's exactly what we found at a population. That overall, when they had at least 20 centimeters of snow on the ground, okay, and that's 7 to 8 inches or thereabouts, right? That basically their stress levels would start declining pretty significantly. And what we know from grouse, and frankly a lot of other species, is that individuals that are chronically stressed tend to do poorer in terms of survival. And even those individuals that are really chronically stressed, they tend to actually pass on those stress responses and stress effects to their young, the generations down the road. Now, the really interesting thing about this is 20 centimeters is roughly the average amount of snow depth that is found throughout Wisconsin, if you looked at the entire state throughout the course of the winter season. Almost all projections basically suggest that in the future, it's going to be more like this. So here we've got basically a species that really needs to have that environment, that microenvironment, to get through the winter environment, and now they're losing it over time. So here we've got this refugia that not only grouse use, but small mammals and plants that is slowly disappearing over time. So there's a story about behavior and how climate change could be influencing that behavior. What about range changes? And so I think all of us can understand that species are distributed in some areas and not in others. And one of the real main predictions of climate change was that if we were looking at, let's say, two species, one being sort of a northerly cold adapted species, let's say the grouse up here in that blue, and maybe a warm, sort of southerly distributed species in the south. And if we had warming throughout the entire northern hemisphere, what we expect to see for that southerly warm adapted species is a shift northward in that range boundary. They're taking advantage of these sort of new climate states, right? If you're a cold adapted species, you'd see basically the same direction, but it's a retraction in that range boundary. So you've got two species here that are basically showing this sort of northward or poleward shift in their ranges over time. And so what we are able to document, or the way we start looking at this, is by analyzing long-term data sets. And one of those is bird atlases. So I don't know how many of you are familiar with bird atlases, but what you can imagine is if you've got a state, let's say Wisconsin, and you broke it up into little blocks, and in this case, 5 by 5 kilometer blocks, you enlist roughly about 2,000 volunteers to go out over 5 years, and they report what species that they are showing up and that they are recording within these blocks. There's over 400 atlases that are being conducted and have already been conducted throughout the world. And the real advantage is that if you've got repeat atlases, you can look at changes in their distribution. So for example, we've got the evening grosbeak here in Wisconsin. We've had 2 Wisconsin breeding bird atlas surveys that were done. One in 1995 to 2005, and one in 2014 to 2019. And what you can see here is basically this idea that you've got evening grosbeak that in the first atlas period, roughly about 20 years ago, that's where their southern range boundary was in the state. Over time, in the second atlas, that's where their distribution is now. So in the first atlas, all those dots is where they were reporting evening grosbeaks. In the second atlas, this is where those grosbeaks are now. And so if you're thinking about that range boundary, you're seeing that shift northward, that retraction for grosbeaks. What about a southerly warm adapted species? So the orchard oriole is a good example of this. This is their distribution in the first atlas. All those sort of dots where we're picking them up. Those gray dots are where we're not seeing them. So what's going to happen in the second atlas? That's their distribution now. So in this case, if you look at that range boundary again, we see that poleward northward shift. As I mentioned, there's over 400 of these atlases that have been conducted throughout the world, and we've been able to look at the signal, the poleward shift, the systematic movement northward of most of these species. And it clearly is one of the most sort of ubiquitous and strongest signs of evidence that we've seen really in multiple parts of Europe, Africa, and here in the United States. So much so that we kind of know that the vast majority of these species are moving at a clip of about 10.5 miles per decade in terms of that range shift. So, think about 30 to 40 years of warming, and we're talking about an entire range movement of multiple species. If you want to see evidence of this, then, if you really want to see this with your own eyes, really the only place you have to look is in your own backyard. Okay? And one of the things we've always been interested in is that if you're looking at the sort of composition of species, are we seeing that there are more of these warm adapted species that are showing up at people's feeders? And one way we've been able to look at this is using a citizen science effort here called Project Feeder Watch. So this is a program that's been running by the Cornell Lab of Ornithology since 1990. And it's a pretty amazing program because each one of those dots you see on the map is a Feeder Watch participant. So there's well over 20,000 people that watch their feeders throughout this winter, and they report what birds are showing up at what time and how many of them there are. So it's a pretty amazing database because you can look at what species are showing up where and how that is changing over time. And so the real question that we had going into it was this idea that if you're a feeder watch participant and you look outside your kitchen window and your backyard bird feeder, you might see sort of a cast of characters like this. So you might have like cardinals and tufted titmouse and Carolina wren. But if you were, let's say, at a feeder or kind of at a backyard in the Mid-Atlantic states, maybe sort of the same sort of suite of species that are showing up at your feeders, but you start seeing maybe some other ones like, a house finch or a junco, or maybe you start seeing chickadees. And of course, if you're in Wisconsin, you might look out and you see a slightly different cast as well. You might start seeing white-breasted nuthatch or American tree sparrow. So it's a more cold adapted species. So when we start analyzing those data to see whether or not we're seeing these shifts in entire communities that are responding to these range shifts, that's exactly what we're beginning to see. We're seeing that some of these species, let's say like the Carolina wren, are becoming sort of more dominant and beginning to show up at feeders and in new areas that they weren't able to sort of previously be. And the species that are really driving this tend to be these warm adapted species that are smaller bodied, that are increasing their distribution and tend to be, generally speaking, more southerly. And so we're seeing this reshuffling of these communities. So these new and what we refer to as no analog communities of species that we've really never been able to document previously. So now we feel pretty confident that when we looked at, not just for birds, but for multiple species in taxa, that more than half of observed animal range boundaries have already shown a response to modern climate change in the direction that we would predict, these poleward shifts. So another sort of important indicator then, we've talked about behavior, we've talked about range shifts, but really another important one is this idea of phonology. And I'm really going to borrow some of the poetic words of Aldo Leopold when describing phonology, because he can do it a lot better than I can. But phonology is that many of the events of the annual cycle recur year after year in a regular order. This year-to-year record of this order is a record of the rates at which solar energy flows to and through living things. They are the arteries of the land. By tracing their response to the sun, phonology may eventually shed some light on that ultimate enigma, the land's inner workings. So it's beautiful prose, and it effectively captures what we know about how the Earth system works. That there's a pulsing, right? A repeatable seasonality to the Earth and how it functions. And so clearly, species have evolved numerous adaptations to be able to take advantage of that seasonality and that pulsing. And so one of the real questions that we've had is that we're in fact seeing changes in that pulsing, in that phonology, especially let's say in terms of productivity or greening up. Are we actually going to see changes in the migration patterns and pathways and the timing for birds? So a good example of this is data that we've looked at for feeder watch, and especially looking at for, let's say, robins here. And so if we can think about where robins are occurring during the winter, when we use that feeder watch data again, we can see that the vast majority of their population are here in the southern United States and along the coast. If we're here in Wisconsin and the upper Midwest, well, during the dead of winter, we may see some robins, but they're fairly few and far between. Right, so that's their distribution in January. That's their distribution in February, much the same. And then what happens in March, you see this big migration movement, right? As robins are leaving their overwintering grounds in the southeastern part of the United States and arriving at their breeding grounds in order to set up their territories. So this idea, this movement of spring phonology and spring migration really was one of the first currencies that ecologists started looking at to see whether or not we are in fact seeing changes, what's referred to as the first arrival of these robins over time, and not just robins, but other migrants. And what we've been able to document is that, yes, indeed, that we are seeing earlier springs in terms of greening up. We're seeing a lot of different sort of earlier spring events, both in terms of sort of the greening up of vegetation, but also for insect emergence. And many of these birds are actually showing that same response. In fact, for short distance migrants, they tend to be the ones that are most responsive. So meaning that they're overwintering in the southeastern United States, and they're really able to take advantage of those warmer springs to move and migrate earlier. So here we've got sort of the proportion of feeder watch sites that are occupied. In the 1990s, perhaps it's coming roughly around sort of the middle of March, and now in the 2000s, maybe it's much more earlier March, or maybe even in some cases late February in those really, really warm years. So the question is, if they are arriving earlier, are they in fact reproducing earlier too? And there's a lot of good evidence to suggest that's in fact the case. That many of these birds are arriving earlier, their whole reproductive cycle is basically churning out earlier. one of the sort of classic studies is looking at tree swallows to this, and in many cases, that they were earlier nesting and be able to fledge their young much earlier. And the way they're able to look at this is actually another cool example of citizen science, where there are these nest record card programs where people, the general public, could go out and record what nest that they're seeing, how many eggs and what species. And they've got a whole treasure trove of this at the Cornell Lab of Ornithology that they're able to mine and actually show that, at least for tree swallows and a few other species, that in fact, yes, those nesting periods are getting earlier and earlier over time. But really the most exciting part that I've been able to see in terms of migration studies has been really the emergence of online checklist programs. So I don't know how many of you are familiar with eBird, but basically eBird is a new initiative only in the last 10 to 15 years where people can record what birds that they see and they hear, and they record it with their own smartphones. And it's really one of the fastest growing biological databases in the world. They get 25 million observations per month. In this case now, you're not just relying on a few observations, you're collecting data continuously throughout the year. So when you can do that, you can actually start modeling out migration pathways at an unprecedented resolution. So here we've got tree swallows, and this is a statistical model that's all built on eBird data to show their breeding distribution. In this case, this is their fall migration, settling in Central America, and then February, overwintering, their spring migration up north, settling back in to their breeding grounds, and so forth. And they can do this now for hundreds of different species. And the real advantage of this then is that we can start seeing what is driving those migration patterns. And clearly one of the ones that we're very interested in is this idea of changes in productivity. So the green wave is this idea that over time and in spring, you get this real sort of blossoming, clearly of productivity throughout much of the northern hemisphere, and fall senescence and winter. So the question is, are birds actually following this green wave? Are they riding the green wave over time? And it is true that most of these birds actually are able to couple their migration patterns with this sort of wave of greening. And we can see this from winter to spring to summer and fall. This is the green up, and this is sort of the bird migration pathway. And here's just one example for tree swallows, suggesting when you get that green up happening in those years where we're getting sort of earlier green up, the tree swallows are able to follow that pattern as well. So what we've seen over time, just like with those range shifts, that for many species, they're arriving earlier, roughly about 2.5 days per decade. And the ones that are really able to take advantage of it are those migrants that are a little bit slower in our migration speed. They kind of arrive a little bit earlier, and they tend to overwinter in more northerly environments. And when I say northerly, they're not going all the way down to Central and South America. So this is kind of sets up an interesting phenomenon for many birds, though, is that they are taking advantage of this greening wave and these earlier sort of spring environments. What's the real problem with this? Well, the problem ultimately is that not all sort of species and parts of the ecosystem are moving earlier over time. And so what we've been able to document is that species like trees and taxa like trees and insects like caterpillars are emerging at a much earlier and a faster pace than the birds are. And so some species of birds are able to track this, but other species are really only timing their migration based on day lengths. And day length is not changing, right? So they're all the way in Central and South America. They start migrating when the days start getting a little bit longer. And by the time they get there, potentially, all this sort of work, all this sort of emergence that has happened in terms of that spring emergence and spring phonology has already happened. And so this sets up a real problem that many scientists call this phenological mismatch. And so the idea here is that if you've got a migrant, in this case, let's say a pied flycatcher in Europe, that its arrival date is kind of right here, and it's always adapted that arrival date to match up with sort of the peak in food availability, in this case, caterpillars. So caterpillars have kind of a boom period, right? Where they kind of take advantage of the bud burst and they start showing up in great numbers. The birds will show up, and importantly, they actually show up right before that peak in food supply. Because it's not really the adults that need that peak in food supply, it's their young. So they come, they set up territories, they basically have nests, and the young are the ones that are really taking advantage of that big food supply. So what's the problem? The problem is that the caterpillars, the Lepidoptera that they require basically show a shift in that phonology of that peak, and it's no longer matching up with that migration pattern for that bird. And this has been documented for several species, and really it's proven quite problematic because some of these species are migrating long distances, like the pied flycatchers going from North Africa all the way to Northern Europe. And so the way I like to think about this is that if you're used to basically coming home at 6 o'clock and having your dinner ready for you, right? And that's kind of, you're ready to eat it. And then suddenly that sort of dinner plate starts showing up at 5:55, 5:50, 5:45, 5:30. By the time you sit down for that dinner plate, well, that food's pretty cold and maybe it's not quite as good. And that's exactly what's happening with these birds. And in fact, the ones that are most mismatched, meaning that they have to travel the farthest distance to get to their breeding areas, they are showing 90% population declines that are due to this phenological mismatch. Okay, so we've talked about this idea of shifts in behavior that could be mediated by climate change. We've talked about range changes. We've talked about phenology. What about the big one, population decline and extinction risk? And again, I'm going to take another example here from sort of our own backyard. I'm going to focus on grassland birds. And primarily because grassland birds, out of all the sort of suite and groups of birds in North America, are the fastest declining group of birds out there. And if you look at their ranges for bobolink, or meadowlark, other sparrows, grassland sparrows, you can start seeing all that red is areas where they're declining. The blue areas are areas where they're increasing. So they're showing widespread declines in their populations, really throughout much of their range. And clearly there's a multitude of different causes for this. One is that we've converted almost 90% of what was native prairie throughout the United States. It's been converted into residential development areas. And that's a major stressor for birds. But at the same time, grasslands are actually where you're experiencing, or where we're seeing some of the fastest rates of climate change. And they're really getting it at both angles. So one, we're seeing a much higher likelihood of extreme weather events that are occurring in grassland areas. At the same time, they're showing drought conditions. So you've got this sort of group of species that are being pressed on one side by residential development and the loss of their native prairie habitat. And on the other side, they're being pressed by extreme events, and another side, they're being pressed by drought. And so you've got this sort of amalgamation of all these different threats for grassland birds. And this is the group of species that we're really particularly concerned about. In fact, almost half of grassland birds we expect to be facing these additional climate-induced pressures over time. And that these grasslands are becoming drier and more exposed to these extreme events, and even species that maybe just a few years ago we considered to be sort of these common species like the meadowlark, we're starting to see actually disappear from many of these areas. So if we look at the numbers, in terms of grassland birds, we've lost 720 million of them since 1970. We've seen a decline of about 53% in their population loss since the 1970s, and about 3 out of 4 eastern meadowlarks have been lost since the 1970s. So we do here in this case really are concerned about extinction risk for grassland species because ultimately they have nowhere to kind of go and move with response to that shifting climate space. And the last example I'll give is disease and how climate might be influencing disease in birds. And probably one of the best examples of this are massive die-offs that we see around the Great Lakes. So I'm not too sure if any of you are familiar with this, but every few years we do see these sort of big die-off events. So here we've got Lake Michigan, where we see thousands of carcasses show up on the lake shore, right? When we get this sort of in a periodic way, and it's definitely getting more frequent in the last few years, the last couple of decades. And it's not just for Lake Michigan, we've been seeing this for other lake systems as well. So that what we've been able to document over time is not just that the frequency of these big die-off events are occurring and being much more frequent, but the magnitude of them actually are increasing as well. So what's causing this? Well, the real sort of smoking gun here is this idea of avian botulism and these outbreaks that occur in these water bird systems. So really the pathway here is that you've basically got this very sort of caustic anaerobic bacterium that develops in sort of warmer lake conditions. When you've got high algae, this sort of leads to these botulism type E events that occur, and it produces this neurotoxin that birds are susceptible to eating. And what that neurotoxin does is it invades their system. It basically leads to a loss of motor control. They get this third eyelid paralysis that starts up with them. They get this sort of drooping neck. It's called a limber neck syndrome. And they actually effectively drown because they can't keep their heads out of the water. And so what it leads to is this respiratory distress. And if you're talking about thousands of birds, you can have these massive die-offs. And really, when we start looking at the mechanisms of this, which a lot of people are studying, is it all starts in this clinopora, in these algae sediments, that then sort of bioaccumulates throughout the whole food chain. And so really right at the top of that, then you have that magnification of that neurotoxin and that bacteria type E, botulism. Right at the top, you've got these whole suite of water birds. So then the question is, how is climate change contributing to this in any real way? And what I would say is what we were able to basically identify is that when you have warm lake conditions, which we are seeing more and more of, and the presence of algae, it basically combined to increase the level of this toxicity and also synchronize these mortality events. Such that when you have very strong sort of warm lake conditions, the presence of these algae, which is generally typical from nutrient runoff, that we got warmer lakes, we had the whole synchronization of these outbreaks of this disease transmission. So this leads us to then back to our sort of our starting point here in terms of thinking about birds as these sentinels of climate change. And I think I've made some pretty good arguments or showed some evidence that when we start looking at all these different components about how birds respond to their environment and the climate change, we've seen behavioral adaptation, we've seen range changes, phenological mismatches, we've seen altered communities, we've seen populations really on the brink, and we've seen this increase in disease risk. And because of this, then, we've got a whole suite of species that are serving as those canaries in the coal mine. And it makes us pause, because next we have to think about what we're going to see in the future. And when we start thinking about all the future projection data, what I would say is that under some of the best case scenarios, and here we've got sort of what's called sort of the current road, the current pathway that we are on. So these are different emission scenarios and our best estimates in terms of future warming. And so if we're looking out into the mid part of the century, we're going to see about a 2-degree warming. So remember what we saw over the last 50 to 60 years, already a 1-degree warming. We're going to see about twice that in terms of the current pathway that we are on. By the end of the century, we're right around 2.7 or 3 degrees warming. Okay, so if we start thinking about where we're heading now, all those different responses I was able to show, all of that was in response to a 1-degree warming. And so now we are just beginning to sort of comprehend what we expect to see in terms of future warming. When we start thinking about what that warmer world will look like, we are particularly concerned about this worst case scenario in the later part of the 21st century. And many of these areas, it's not just that the overall warming of the world may be 2 or 3 degrees warmer, but like I mentioned, those Arctic areas could be looking at 4 to 6 degree warming trends by the end of the century. And those precipitation patterns, certainly with those dry areas becoming even more dry, those wetter areas becoming even more wet will continue. The real concern that climate scientists have is not necessarily just the warming that we're seeing that are being influenced by human modification. It's the idea that we are heading toward the planetary tipping point. And really, when you look at it in terms of the climate system, about 10,000, 12,000 years ago, we've been existing sort of in this cradle of the climate system between sort of a deglaciation event and what was a relatively stable climate for the last 10 to 12,000 years. This cradle of that climate system basically allowed us to create societies, agriculture, and most of the species that we've been interacting with have adapted within that cradle itself. but we are hurtling towards this sort of new planetary threshold. And they call it the tipping point, because ultimately what's going to happen is we're going to get to a point where there are certain feedbacks within the climate system that are going to click in. So, and when these feedbacks click in, we're going to enter a new sort of stable state of warmer temperatures, mega droughts, flooding events, earlier springs, and a loss of snow cover. When we start thinking about the future birds then, we are projecting what's going to happen with their winter grounds and what's going to happen with their breeding space. And so what we can start doing is projecting what's going to happen, let's say for the common loon here. This is their current climate space here, that sort of blue outline. This is their summer range. And you can start seeing where we project that climate space is going to be in 2050 and 2080. We've got loons in Wisconsin right now, right about here. That climate space is not going to look too good for them by the end of the century. When we've looked at hundreds of species, about 300 species will lose more than half their climate space by the end of the century. So this isn't just something where we're worried about just a couple of species. We're really worried about a whole multitude of them. So I'll come back to this idea. Birds are awesome. But the question is, we are pushing them to the limits of that awesomeness. And so what can we do in terms of those sentinels, those canaries in the coal mine, to prevent what is effectively a harbinger of what's to come? And so I'll leave you with a couple sort of, I think, important action items when we think about conservation in sort of this new phase of climate change. The first is degrees matter. I think this is an important component here. That when we start thinking about trying to keep warming to 1.5 degrees or 2 degrees or 3 degrees, these are not arbitrary levels. Okay? When we start thinking about the proportion of birds that are going to lose more than 50% of their climate space, of their range, under 1.5 degree warming, which is a pretty good sort of best case scenario, we're talking about maybe 10% of those birds that are going to lose more than half of their climate space. Under 2 degree, we're kind of shooting up a little bit more to about 20%. But the real jump happens around 3 degrees. And that's when we're going to see roughly about 0.4, and in some cases, if we go even higher, almost half of all birds throughout the world are going to lose more than 50% of their climate space. And so trying to kind of take refuge in this idea that trying to make changes now so that we are basically trying to hit some of these targets will have real benefits down the road. The other kind of component I hear quite a bit is that birds will kind of simply adapt, right? Birds have kind of been around for quite a long time. They've gone through glaciation events, they've gone through deglaciation events, pretty amazing changes in the climate system. And so that canary in the coal mine can effectively just put on that gas mask and not have to worry about anything, right? There's two problems with this line of rationality. One of them is that the rate of warming that is basically being experienced is unprecedented for the last 2,000 years, and certainly maybe even going back farther than that. And so all these species have developed adaptations to basically deal with climate change. That's absolutely true, but nowhere near that rate of climate change. And then the other component here is that when these experience climate change and past geological events, they've had room to roam. They've been able to sort of move with that climate space. But we have manipulated and changed the Earth's surface dramatically. Almost 45% of the Earth's surface, the land surface, we've converted to agriculture. So now you've got a species that is trying to move with their climate niche and their climate space over time, but they can't because they don't have the habitat to do it. However, I would say that when we talk to managers and we talk about sort of this idea of climate smart conservation, really oftentimes we are not trying to reinvent the wheel of conservation here. We're talking about identifying refugia, areas where maybe the rate of warming is not quite as bad. We're trying to think about what kind of habitat management tools can be enacted in order to, let's say, manipulate water levels so that species can be less susceptible to flooding events. Maybe we're talking about translocating a species that are maybe more drought tolerant or drought resistant. We're talking about changing harvest quotas. We're thinking about protected lands, not now, but maybe in 50 years down the road. We're talking about managing those diseases, the ones that are most susceptible to changes in the climate space. These are not new tools. These are all ones that we've been working with, frankly, in conservation for the last 50, 100 years or more, but we're trying to put that climate change lens on top of conservation so that people can start understanding, managers can start understanding that it's not a problem that's occurring throughout the world, it's something that is occurring in people's own backyards, and there are actions that they can take. In terms of what you can do, if you're not one of those managers out there trying to think about managing or conserving a piece of property or a species, I would say that there's some important action items here that I'll kind of suggest that everyone to think about. One, clearly one of them is being energy efficient. All right, there's no way we can think about making those degrees matter unless we tackle some of these problems of mitigation. All right, so think about in your own lifestyle how you can be more energy efficient. The next is let's make it an issue. I think there's been a long-standing tradition where on almost all public surveys, people think about and are worried about environmental issues, but rarely do you see it up in presidential debates. I think that's been changing over the last 5 years or so. But what I would say is that we need to continue to make it an issue that's just as important as other political and social issues of the day. Tell stories, talk to your neighbors, talk to people that may be skeptical. Don't even use the term climate change. Okay, because what we can effectively do is just tell those stories that we see in our own backyards. When we think about the species that we start showing up that we didn't see before, species that we used to see and we don't see anymore. Those are much more effective stories, a much more effective way to talk about this issue than talking about something that's sort of broad and politically charged as climate change. And then I would say, if you're not already, become a citizen scientist. I don't know if you noticed this, but pretty much like 80% of this presentation was based on data that was collected by the general public, by citizen scientists. If we didn't have citizen science dating back 30 to 40 to 50 years, this would have been a much shorter presentation. So think about joining those programs, iNaturalist, eBird, Feeder Watch. Those observations, those data that citizen scientists are collecting and contributing really are the backbone for being able to say anything about climate change. And last but not least, I'd love to stand up here and really say, I did all this. I didn't. This was really the culmination of all the hard work and passion of all graduate students and postdocs that come through my lab and worked very hard, are passionate, and I'd love to see them kind of continue through graduate school, go on and do fantastic work, and of course, my critical friends and collaborators in our department and the university. And with that, I'd be happy to take any questions. Yeah.
I don't hear you talk anything about the ecosystem services that the birds. I don't hear you say anything about the ecosystem services that the birds do. I was thinking particularly of the phenological mismatch between caterpillars and the birds that eat those caterpillars, because if those birds aren't eating those caterpillars, what's happening to what the caterpillars eat?
It's a great point. So if anybody didn't hear that about the ecosystem services that are being affected by all these changes in bird populations, and absolutely true. So when we talk about ecosystem services, the idea is that certain natural relationships and species clearly provide benefits to an ecosystem, and frankly, can provide societal benefits as well. So things like pest management. You know, we talk about this all the time in our cultural settings. Well, birds and insects, and clearly bats, play a really important sort of natural role in being able to keep certain insect populations or pest populations down. Another one is clearly pollination services, right? So we think about bumblebees, right? And the fact that most bumblebees populations are collapsing, and birds are no exception to that. They play a critical role in most of these ecosystems, being able to pay off those ecosystem services, not just in terms of things like pest management or keeping certain pests down, but also clearly they play a role in terms of how we interact with nature. And things like, 35 million people in this country feed birds. Okay, that's a pretty amazing number when we think about how many people participate and really value those species showing up and interacting with them. And so I think that's an important service that, yeah, definitely we think about trying to capture, and it's clearly being effective.
I was going to go back to your very first slides, and I'm going to sort of play the devil's advocate here. Well, one thing I've often wondered is if passenger pigeons were still around, wouldn't we consider them a fairly serious health hazard? And then the second part of my question, what is wrong with cats consuming birds? Isn't that just part of a natural process at work? Thanks.
Sure, that's a good question. The passenger pigeon question in terms of like the health, it's hard to know whether or not they would effectively be like a health hazard, other than the fact that, yeah, they clearly showed up in pretty massive numbers, right? And they were clearly following, in some cases, masking, it's happening in trees. And so they would kind of be following the masking events. And so absolutely, those are the pretty amazing species when you think about it, that we were able to decimate them and effectively push them to extinction. In terms of the question about cats, what I would say is that, yes, there's been a number of studies out there that have showed the disproportional effect that having a domestic cat that can have a bird population. And it is not necessarily like a natural predator as you just think. Birds are absolutely adapted to their natural predators. They have many sort of cues associated with being to avoid, let's say, hawks and things like that. Cats are not one of those natural predators, especially in places like North America. So I would say I am a proud owner of 2 cats. I keep them inside. And so I would say that if you do own cats, that keeping them inside has many benefits, but probably primarily that they are not decimating bird populations. And what I would say is that there are people who have really quantified these numbers, who have really actually tagged cats, followed them along, seeing how many birds have extrapolated those numbers. It is remarkable how efficient they are at taking out birds. And when you basically multiply those effects, we're talking about billions over time. So, yes, I don't want to start a huge thing, but I will say that I think you can still enjoy having a domestic cat. Just try to keep them indoors.
Other questions? Andy?
Well, we had a presentation about the stats of birds, listening to the audio of birds, and I was thinking of how you measure their stress level. I assume that recently you've been measuring the fecal material as opposed to getting the blood sample. And so, given you listen to the audio of the birds, could you also look at their eyes and for more citizen science of looking at the stress of our birds?
So the question is a really cool one, right? So the question is, one, how do we measure stress? And absolutely right, that for grouse, we would pick up their fecal samples, which were conveniently in snow, so pretty well preserved. And so you can actually get corticosterone levels pretty acute in a pretty accurate way using fecal samples. The best way clearly is blood, but if you're trying to do something non-invasively, fecal samples are the best. In terms of other ways to actually capture stress, yeah, that's a really good question. If whether or not there's other sort of non-invasive way that citizen scientists could either pick up, things like, thermal imagery is a big one. So what we do know is that when birds are stressed out, they will shunt blood to sort of the interior of their body. And we actually have thermal imagery that shows this, which is pretty cool. So there could be ways to think about that. But yeah, capturing stress in a real-time sort of way is pretty complicated to do. And being able to associate that with something like chronic stress versus an acute stress response, like a hawk comes by and you're showing some sort of stress response, is they're 2 different things.
Would I be correct in assuming then that the 3-degree differential in rise in temperature is going to be the canary effect for the birds?
I'm sorry, so the 3-degree is going to
Well, you mentioned that the 3 degrees
Yeah,
seems
it's
to be an
the-
exponential rise in the depopulation of the birds. And at that point, is that literally the canary effect that we get at from the birds themselves.
Yeah, I would say so. So the question is 3 degree kind of that canary effect? Is that the game changer? For birds, I would say yes. So I think that is really what most estimates look at in terms of some case, the worst case scenario. Certainly very possible scenario, but definitely the worst case scenario. I will counter though, or I will add this little caveat that for insects, it's more like 1.5. It's more like 2 degrees. So when we look at the benefits in terms of saving it from a 1.5 or 2 degree warming, we're talking almost 66% change for insect population. They are going to be much more effective than birds are. So if we are thinking about those great canaries in the coal mine, other than birds, there's a whole host of other taxes that are even more sensitive to climate change effects. And so, but yes, I would say 3 degrees for birds in particular is something that we think.
So then, therefore, then as an issue with the insect or food for the birds,
Absolutely.
that's going to show up before even the temperature differentiation then.
I totally agree. I totally agree. When that 3 degrees and what I showed you in terms of that degrees matter is really trying to say how much of their sort of climate space is going to be left in the future, right? But even if a species, let's say, doesn't lose 50% of their climate space, they may already start showing some of these effects due to changes in insects and their food resource. Yeah.
Yeah, thanks. Okay, I'm going to raise a subject that's considered taboo in many circles, and that's you're using the statistics on ppm of CO2 and in the atmosphere. I mean, definitely that needs to be lowered, but can that be achieved without some type of corresponding reduction in the Homo sapiens population of the world? And why is nothing being done to tackle that aspect of the problem? Thanks.
Yeah, it's a good question. So the question is, okay, well, are people effectively the problem? You know, especially if we're talking about trying to mitigate, you know, what is well above 400 parts per million in carbon dioxide. I mean, I'm a bit outside my area of expertise, but I would say a couple of things. Is that one, I do think overpopulation really was a concern 40 to 50 years ago, and that clearly was a big sort of part of the debate. I think that has changed considerably, and for a couple of reasons. One, we've clearly seen population growth rates, especially in the United States, really kind of start going down. And so I think that is one aspect of it. The other aspect of it is that it's not necessarily population growth, at least, you know, again, in my own opinion, it's really effectively how we basically use and consume resources on the landscape, right? And so when we talk about things like, for example, in the US, a couple of years ago or a few years ago, we were very proud because we actually started ticking down on our CO2 emissions in terms of like the gigatons of carbon that was being output by the US. And we started patting ourselves on the back. But what we actually didn't really see was that we were effectively exporting that CO2 because we were importing so much from developing countries. So places like China, India, right? So we were still responsible for those gigatons of carbon dioxide. We were just importing all that CO2. So what I would say is that, yeah, I mean, I still think clearly when we start thinking about population growth, it is something that is part of the conversation, but I would say clearly part of it is how we sort of function as a consumer nation and what we need to do about that. In terms of reducing those levels over time, I do think at some point we are talking about pretty sort of technological advances that maybe, you know, we're really going to have to see in the next 50 years or so.
There's a professor at UNC that's developing an insect food base for birds as a leading indicator of what's going to happen to them.
Yeah, excellent. Oh, is that maybe Alan Herbert? Yeah, I'm not sure. Yeah.
I was very surprised at your statement crediting citizen scientists data with 50–60% of the data presented in your talk tonight. I'd like to throw some gasoline on that fire. People who are listening to this, how can I ask Wisconsin 4-H state specialists help bring more people to you and your colleagues to be collecting more data, more reliable data?
So I'm sorry, the question is like how we can think about doing better data or
How
more?
can I help recruit people to
Yeah.
do this for you?
It's a really interesting thing. So when we talk about citizen science, there's a real difference between recruitment and retention, right? So we can oftentimes get people very excited about doing a program, but really the goal data that we think about are these programs that we enlist people, we keep them in the program. And because what we've seen with data quality is just first year you do it, it's kind of okay. But then you get used to it and those protocols, and that's when data quality really shoots up. And so keeping people in programs, getting them excited is really one thing. The other thing I'd say is that trying to recruit different kinds of audiences. So for example, Snapshot Wisconsin. It's a program that I was part of developing here in collaboration with the DNR. We've got over 2,000 people that go out and put camera traps on their lands. And we've done really a lot of amazing work with some of this data now. Snapshot Wisconsin basically has a whole different audience than eBird does, right? So and primarily because it's just kind of what different messaging that goes out. And so what I would say is that we need to diversify our citizen science programs, think about trying to tap new audiences that maybe even ever heard of citizen science before, and start sort of diversifying that base. So yeah, I mean, I'd say reaching out. What I would say is that the sociological data on it, psychological data, suggest that most people do it because it makes them feel good, that they feel like they're doing something good, and it's an important activity for them.
Be happy to talk with you about that.
Sure.
Week after week, month after month, it's a big deal.
It is.
For sustained project-based learning for the young people, Wisconsin 4-H and other youth organizations, and then for retirees.
To make a program really successful and to keep going, it takes a lot of funds, a lot of money, and dedicated people to do it.
I had a question. So your main thesis is really that habitat loss through global warming essentially is what's causing the birds to migrate. I want to know, what are your thoughts about other possibilities, such as different farm chemicals are used that reduces the population of insects, or different lighting that's used that keeps the bugs down now, because they have blue lighting or LEDs for streetlights.
Absolutely. I mean, so tackle maybe the lighting component first. What we started looking at when I was analyzing eBird data a few years back, we saw this really kind of weird effect where migrant birds started showing up in urban areas during autumn migration. And we couldn't really explain it very well. And what we've shown with sort of some current studies is that, especially during migrant, they are kind of funneled into urban areas because of the light effect, kind of like a moth ground flame. And the real problem with that clearly is that you get window strikes. And so when we start thinking about migration patterns, we are starting to quantify or try to measure how much that light effect sort of brings a lot of these migrants in. What I would say, one of the sort of craziest examples of this was the 9/11 memorial in New York City, which is basically two rays of light that's shown up in memory of 9/11. And there was all these studies actually that showed that birds were flocking to these big rays of light and affecting their migration pattern. And what's been remarkable about that kind of work is that it's a very easy thing to change. You can basically turn off lights, especially in skyscrapers above a certain level. You can do it at different times of the year when certain migrants are coming by. So something that can be very easily remedied has actually already started happening in a lot of different areas in cities. So that definitely influences migration. I don't know if it's really influencing necessarily the timing of migration. So we haven't necessarily seen birds that are shifting or the pattern or the phonology of that migration with respect to sort of with respect to urban lights. We just see kind of how it may be changing their pathway of migration. In terms of the farm chemicals, absolutely. I mean, I don't know as much about that, frankly, as I probably should, but it's definitely something that I know people have been concerned about.
I saw on my Twitter feed either yesterday or the day before, there was a mass death event among migrating birds. That's all I saw was a tweet. Can you fill us in on, did you hear this and had to do something?
Yeah, so there, I don't know if it's the one you're talking about, but out west there have been these sort of mass die-offs, and people were wondering if it was associated with things like the wildfires and air pollution, air quality that was happening. And I think I think this is still going back and forth a little bit. My memory is twofold. One is that the air quality associated with wildfires is definitely having some effect. But also I think there was like an extreme event in terms of a cold snap. And what we have seen with some of these migration patterns too, is that when it does line up migration with an extreme event, like a big drought, or a big hurricane or something like that, you can absolutely have these alter migration sort of patterns for a given year.
Thank you. Any other?
And just kind of follow up on that. One thing that's been documented is that wind farms can affect migratory patterns as well. I just want to, I guess, ask you the question: what could we do better for the wind farms? Because that's a part of the equation, right? And
yeah, so I would say stay tuned. I know a couple of people who are really focused on this idea of basically airscapes. So like we think about landscapes, right, where we think about preserving habitat for birds on the ground, and there's a lot of work right now in preserving airscapes. And I think the idea is that there are maybe potential in the way that you think about turning off lights in skyscrapers, right? Whether or not you can stop rotaries going, during certain times of the year. So what they're really doing is kind of neat work. It's called birdcast, where basically we use data from eBird data and even weather surveillance data, like radar data that you use to kind of capture, radar, like, storm events, to pick up when birds are showing up in the atmosphere and then doing forecasts 1 or 2 or 3 days before their migratory front shows up at places. And so I say stay tuned because some of that work to me is really going to be exciting over the next 10 years.
Just to put midterm thing in perspective, what is the percentage of birds that are killed by windows in our buildings relative to wind turbines?
I don't know off the top of my head. I don't have a good intelligent response to that, other than I know it is something that people are concerned about.
Yeah, and the professor you mentioned is the one at USC.
Alan Herbert, yeah.
Yeah.
And Kyle Horton is the guy who's doing a lot of this aerospace work and birdcast. He's at Colorado State.
I have a question from the chat. We in the US are mandating that we have net zero emissions by 2050. And we may even have negative CO2 by the end of this century. Do you think, given this, if you do tracking of birds on a seasonal basis, say from 2030 on, do you think we should see a reversal from the decline in the populations observed now?
From understanding that correctly, so if we are successful in being able to curtail CO2 emissions, would we actually see a reversal of some of these trends? Like how quickly might we actually see, let's say, things like migration actually respond to that? It's a tricky question in a sense. I do think that probably some of these phenological cues, they may respond pretty quickly to if they potentially, do change over time. I would say this though, that the CO2 emissions that have been pumped into the atmosphere over the last, 100 years or so since the Industrial Revolution, if not longer than that, take a long time to dissipate. So, in terms of these earlier spring phenomena, I don't necessarily see that even if we basically cut CO2 emissions, which I'm kind of doubtful tomorrow, that we're certainly going to see a reversal of that in the year following that. I think some of these effects are basically locked in some respect or not, certainly over at least into the mid-century. But yeah, I mean, I think, specifically whether or not birds might actually respond, or if you start seeing that change in the earlier spring events, I think some species may respond to that pretty quickly.
Second part of the question was also, will preserving the DNA of threatened birds now and then reintroducing them after 2050, will it rejuvenate a healthy bird population?
Probably not, but it's an interesting thought experiment. I think we do talk about, basically preserving genetic material for species that we feel very strongly are going to go extinct in the next 10 years or so. And so whether or not we can basically do de-extinction, it's a bit outside my area of expertise, but definitely an interesting area.
Any other questions?